Hello. Hi, everyone. Hi, Saurabh.
Hello.
This is Nashil, founder and CEO of CryptoNaukri.com. So, today we have Sourabh Aggarwal. He is blockchain developer and an educator. He is a gold medalist in computer science from Indian Institute of Technology, Palakkad. So he's going to conduct this workshop on zero knowledge. So uh, all the best, Saurav, and I hope you guys will learn a lot of things from this workshop. So I'm handing over this workshop to you, Saurav. Please.
All right. So, hello everyone. I hope that you are ready to gain zero knowledge today. So, zero knowledge proof. What is it? In cryptography, a zero knowledge proof or zero knowledge protocol is a method by which one party, which we will call as the prover, can prove to another party, the verifier, that they know a value x without conveying any information apart from the fact that they know the value x. So, on a philosophical level, they are part of a set of new cryptographic tools that show that transparency does not have to be in conflict with privacy. Let's look at some examples so that it is more clear. For instance, you all are viewing this session right here. Now, suppose a student wants to give a review of an instructor, say me, but he or she wants to give it anonymously. So, with ZK proofs, the student can prove that he or she is indeed eligible to give a review. Basically, the student belongs to the class and they can do that without revealing their actual name. So anonymous reviews in a class, student can give a review for an instructor anonymously by proving that they are eligible to give reviews, that is student belongs to that class, without revealing their identity. Similarly, let us look at this example, COVID-19 test. You can prove that you have recently tested negative for COVID-19 without revealing the exact date you were tested or on which lab, etc. You only reveal that you were tested within a requested window of time at an officially recognized location, nothing more. Similarly, an exchange, etc., can prove that they're solvent. Basically, they have more assets than their liabilities, and they can do that without revealing anything about their assets, besides the fact that it matches their liability. Similarly, you can pay your taxes without revealing anything about your financial data. So ZK proofs helps us enable write such decentralized applications. Also, like let me first tell you a bit about these two types of ZK proofs. One is interactive and the other one is non-interactive. In interactive, we have to and fro communication between prover and verifier. The verifier gives the challenge and a prover gives back a response. The verifier then again gives a challenge which can depend on the previously received response, and then the prover again gives a response, and so on until the verifier is convinced whether the proof is valid or not. I mean, whether the prover indeed possesses the required knowledge or not. Now, we also have another type known as non interactive, and our focus will be on this type. So, what is this non interactive? Prover gives a proof to a verifier, which the verifier checks and let prover know whether it is valid or not. So, no further interaction. Just one thing. Prover gives a proof and verifier tells whether it is valid or not. That's it. So this is suitable in the sense that smart contract can act as a verifier to which prover gives a proof and receives back the response. This is far better than having a smart contract, doing this to and fro repeatedly many times between this prover verifier. This is far better, and this is what is mainly used in this blockchain world. Moving on regarding the scope, so we have this. So somebody asked, what privacy preserving technology do you think will be the most widely adopted, consciously or unconsciously, by the majority of netizens in 2050? So Vitalik replied, I expect zkSNARKs to be a significant revolution as they permeate the mainstream world over the next a decade or two. So to understand more about the relevance of zk proofs, maybe you can try searching about these terms: zk rollups for scalability, and we also have this tornado cache application for privacy. Zk rollups are considered as a perfect solution to this scalability problem. And if I were to give you a very high level idea about this zk rollup, then zk rollup bundles the transaction and executes them off chain. It then generates a cryptographic proof known as zero knowledge proof for the hundreds of transactions it has settled off chain. So prover is an off chain web service, and then this proof gets submitted on the layer 1 chain for validation, and the verifier in this case will be an on chain smart contract which will see whether it's valid or not. So this is how zk rollups work, and therefore we can see that zk crypto enables one to do new things that weren't possible before. Dapps shouldn't be just about doing existing stuff better. Better will be that we can add some additional possibilities. Also, if I were to give you like this zk rollup, what I have mentioned here is like a very very high level idea. Similarly, for the tornado cache, if I were to give you a just a high level idea, will be user deposit funds. Suppose we have three players and all three are depositing same amount of fund. The In the newer version of Tornado Cash, the funds can be indeed arbitrary. Uh, I heard that they are using something like UTXO model there, but for the simpler implementation, the classic Tornado Cash, or everyone is depositing the same amount of funds, say 1 ether. So three people have deposited all the this 1 ether, 1 ether, 1 ether. So the pool has 3 ether. Now somebody comes and takes 1 ether from that pool. We will not know, the one who has taken the money from that pool, which of the three participants the person is. So with the help of zkSNARKs, we are able to achieve this. There are of course many other things. There are relayers, because the withdrawer will be calling the the withdraw function, and then the withdrawer will require some gas, etc. So as to avoid that, we have relayers also in tornado cache. I mean, there are other things, so let us not go into that. Don't worry if you did not understand this tornado cache thing. That's not the focus of this session. Now we will move to this zkSNARKs. So let us first understand about this arithmetic circuits. zkSNARKs permits proving computational statements, but they cannot be applied to the computational problem directly. The statement first needs to be converted into the right form. Specifically, zkSNARKs require the computational statement to be modeled with an arithmetic circuit. Although it may not always be obvious how to do this conversion, most computational problems we care about can easily be indeed converted into an arithmetic circuit. An FP arithmetic circuit, this is basically a field containing all the elements from 0 to p minus 1. I hope that you are familiar with these abstract or like modern algebra concepts of groups, rings, fields. So if I go in introducing field here, that will not be, that will take so much time. So if you are not familiar with fields, I would suggest you to look about them, because they are very essential in understanding the application part of zkSNARKs. So an FP arithmetic circuit is a circuit consisting of set of wires that carry values from the field FP and connect them to addition and multiplication gates modulo P. So I hope you are also familiar with this modular arithmetic. So regarding this arithmetic circuit, I will be going to this link now to show some other thing also. Okay, I think it is visible. So an arithmetic circuit over a field f and the set of variables x1 to xn, where of course these all are variables in that field f, is a directed acyclic graph as follows. every node in it with in degree 0, basically these leaves things. This is called as an input gate and is labeled by either that variable name or a field element. Every other gate is labeled by either plus or multiplication, since in the field, which is it's like some things, I mean, base structure is the ring, and in the ring we have this group addition and this ring multiplication. So that is these two binary composition operations is what is available in a field. So in the first case it is a sum gate, and in the second it is a product gate, I mean this plus and this multiplication. An arithmetic formula, this thing is not relevant, but if you want to read, an arithmetic formula is a circuit in which every gate has out degree 1, and so the underlying graph is a directed tree. A circuit has two complexity measures. Basically this size 1 is what I will use later also, so let us read that. So has two complexity measures associated with it, namely the size and depth. The size of a circuit is the number of gates in it, so all these input gates, this and etc. And the depth of the circuit is the length of the longest directed path in it. For example, the circuit in the figure has size 6, so 1 2 3 4 5 6, right? And the depth is 2. I hope that is clear. This part is what I'm mainly interested to show regarding this polynomial. So like the polynomial defined by the circuit. An arithmetic circuit computes a polynomial in the following natural way. An input gate computes the polynomial it is labeled by. A sum gate V computes the sum of the polynomial computed by its children. A gate U is a child of V if the directed edge VU is in the graph, basic graph theory. A product gate computes the product of the polynomials computed by its children. Consider the circuit in the figure. For example, the input gates computed from left to right, this x1, x2, and 1. That is what we have, x1, x2, and 1. The sum gates compute. So this one is computing x1 plus x2, and this one is computing x2 plus 1. Right? So they compute x1 plus x2 and x2 plus 1 respectively. And the product gate will compute the output of this plus gate, which is x1 plus x2, and there it is having the another input, so into x2, and then another input is this x2 plus 1. So this is the polynomial computed by this circuit. In case anyone has any query, you can raise a comment or interrupt in whatever way this software is allowing. Moving back to where we were, we saw this arithmetic circuit thing, so let's move on. Now regarding this magic, you might be a bit curious that how is this magic possible. So to give you a gist of it, like an high level idea of how it is possible, we have this homomorphic encryption, right? So let's see that. So suppose Alice wants to add two secret numbers x and y, where these x and y are belonging in the set of natural numbers. So when I say natural numbers, I'm also including 0. So z positive union 0. Equivalently, in some FP, like as such, if they are in natural numbers, I can have them contained in some FP for large enough P, basically this prime field P, right? But she wants to add these two numbers, but she lacks the corresponding computational power. So, what homomorphic encryption is allowing us? She sends h of x and h of I to Bob, encrypted such that Bob doesn't know private key to decrypt. So, here also assume that this h is a good hash function, basically one way and having strong collision resistance. I hope you know this one way. Basically, once you have computed h of x, it is computationally sort of impossible to find the pre-image x. Similarly, strong collision resistance means it is computationally impossible to find two inputs x1, x2 such that their hash image is the same. So Bob, after receiving h of x and h of I, he has the computational power. He does this h of x plus h of I and returns the result back to Alice. Alice then decrypts this h of x plus h of I to get x plus y. This is normally not seen, but in case of homomorphic encryption, it is preserving the addition. That is, h of x plus y equals to h of x plus h of I. So this is the power of homomorphic encryption. So suppose this was true for any arbitrary polynomial f defined by an arithmetic circuit. That is, h of f of x comma y equals to f of h of x comma h of y. Now, suppose I have this problem given an output y, which is belonging to this prime field, and a function f defined by an arithmetic circuit. Prove the knowledge of a secret value of x such that f of x equals to y, given that such a x exists, right? So I want you to think for a minute. I want you to think for a minute how a solution to it can be. Fine. So let us wait for a minute. We are 30 seconds in, just 30 seconds remaining. All right. So minute is done. So this is the solution. Verify being satisfied with the mathematical properties of h. Prover can reveal h of x, not x. Prover can reveal h of x and perform all the computation like this f of this thing to get h of y. Now, verifier can verify this whole computation starting from h of x, everything, this whole computation, the verifier can verify, and verifier will check that indeed in the end you got that h of y equals to this, the end result of this computation. So, this is the solution. So, sort of, this is the magic of homomorphic encryption, of how this zkSNARK proof is possible. Notice that here y was public and x was private. This distinction will be explained next, but you can very clearly see that this y was given. So this y was public and x was the knowledge the prover has to prove of. So this x was private. So moving on, an arithmetic circuit takes some input signals, perform computation, and gives out output signals. Every other signal is an intermediate signal. So the output of every addition and multiplication gate is considered as an intermediate signal if it is not an output signal. So if I show you in that diagram of Wikipedia that we saw, let me move the here. Okay. So here the output of this plus gate and this plus gate will be an intermediate signal, and that final output of this whole circuit after this multiplication gate will be our output signal. Okay. In Circom, so this is the language we will use to write circuits. In Circom, all signals are by default private. So first, I want you to understand this clearly, or like have this strongly ingrained, that all signals are by default private, and there is a restriction to which signals you are allowing to be public. So let me tell about that restriction. There is something known as main component. Fine. Just for now, understand that there is something known as main component. For this specific component, this main component, its output signals will be public. Fine. So one thing which is public is the output signal of the main component. Second thing which can be public, so output signals are public for the main component, and some like input signal, it is up to the circuit writer which of the input signals he or she is allowing as to be public. So all output signals are public and input signals can be specified as public. So you can specify which of the input signals you want as public. Rest all signals are private. So all these intermediate signals and every other signal, that all are private. So I hope this part is clear. We will see examples and then it will become more clear. Just give me 1 minute. Okay. A signal being public implies that verifier knows them. So, in case you are slightly confused, what is the relevance of making a signal either private or public? So, a signal being public implies that verifier knows them. And in cases, verifier might set some of them. So, some of the public signals might be set by the verifier. Like in that case, the Y was set. Now, prover has to prove knowledge of private signals. So this is what we call as, you can think of this as argument of knowledge, such that these private signals, so prover has to prove the knowledge of these private signals, and these private signals along with public signals, which I'm going to denote by P for the rest of the slide. So make that note, that public signals I'm denoting by P. They satisfy all the constraints of the circuit. This constraints term I have not explained, but while writing the circuit in this Circom, we specify the constraints. Suppose that this value has to be that, etc. So all these private signals along with the public signals, they should satisfy the constraints of the circuit. So what the prover will prove essentially, that he knows some private signals, that he or she or whatever entity knows the private signals, such that those private signals along with public signals satisfy the constraints of the circuit. It might be the case that a given that the constraint set, the possible solutions for that constraint set might be multiple, not just a single. So the prover has to just prove that whatever the private signals the prover has along with those public signals, the constraints are satisfied. So that is the circuit satisfiability. This set of signals, these private signals plus public signals, is what is called as witness. And this witness I will denote as W. So this witness is like a secret, right? You don't want to leak your witness because it has your private signals which you don't want to reveal. So now moving on to the constraints part. So let us understand the constraints part. Circom allows one to specify quadratic constraints. Not, you cannot write any constraint. You have to specifically write only quadratic constraints between various signals. So between various signals. So let us see how is that. So a quadratic constraint is of this form. We have this pair of parentheses multiplied by some another pair of parentheses plus a third pair of parentheses. So we have this SI, all this SI which you can see here, that forms the set of all signals of the circuit, right? All the public, private, all these input, intermediate, output, whatever, all the collection of those signals is what I'm denoting as this SI set. So to that SI, I multiply any field element AI, and of course I'm doing this summation from I equals to 1 to n for these n signals, assuming there are n signals, right? Multiplied by again this another linear expression, this bi into si. So we have this another linear expression, then plus some linear expression, right? So in case, so for the quadratic expression I cannot have like this: S1 into S2 into, say again, S2. So S1 into S2 into S2. This is not quadratic. How can you put it in this form, right? You did S1 into S2 from here, but how will you now do into S2 again, right? So that is not quadratic. That perhaps would be called cubic constraint. So what we have is quadratic constraint. Of course, these ai, bi, ci can be zero. You can have all of these ai, bi 0. So suppose the constraint s1 plus s2 equal to 0. So that is a valid constraint. Now, this set of all constraints describing the circuit is what is called as rank 1 constraint system. So the terminology is this, that the set of all constraints describing this circuit is called rank 1 constraint system. Now, this is like the important part about zkSNARK. So the full form of zkSNARK is zero knowledge, succinct, non, this S first of all stands for succinct, N stands for non-interactive, AR for the argument, and K for knowledge. So succinct, non-interactive argument of knowledge. So this argument system is a triple SPV. So for the succinct part is what I'm trying to explain in this slide. So regarding this succinct part, we have this triple SPV, right? So to this S, we give this the rank 1 constraint system and a random security parameter lambda. This thing is called as random security parameter, which I will explain later, right? And verifier generates these lambda. Of course, I mean, it will become clear. So to this S, if I give these two things, I get a prover's key and a verifier's key. So these two things I get, a prover key and a verifier key. Now to this prover, if I give, if the prover use this proving key and the witness, so if the prover uses this proving key and the witness, what the prover will get is a proof. And what the succinct part implies that the size of this proof is asymptotically bounded, this big O notation we have, to the logarithmic of this size of the circuit. So when we are using this mod symbol C, what I mean is the size of the circuit. And what is the size of the circuit is what we saw, right? I showed you the definition. So this size of the circuit and this random security parameter. So log is finished, and then comma this size of the public inputs. I mean size of, sorry, not public inputs. I mean it is also called as public inputs, but in our terminology it is public signals, right? So if I show you, and these public signals, right? So the output signal of this main component can also be public. So all the public signals, input signal, the public input signals and the output public output signals, so all that is P, and the size of that P is what is being talked of here. And so I have told you that C denotes the size of the circuit. And then we have this verifier, which will take the verifier key, and then it is going to take the public signals. So here you see that it is not taking witness or private signals. What the verifier is taking is public signals, and in case of witness it is using pi, the proof, right? So then the verifier will tell whether this proof is valid or not, I mean satisfied the circuits or not. So either accept or reject. And the succinct part, besides this size of pi, the succinct part also implies that the time the verifier takes to verify is asymptotically bounded, this like this, the size of p comma log of this, right? So this is the succinct part. Now, if this SPV is also zero knowledge, that is, we learn nothing about the private signals, besides, of course, the fact that they satisfy the circuit along with those public signals, then we say that it is zkSNARK. So, I hope with this you have received the, the high level idea about zkSNARKs. Now, there are different protocols which implement this SNARK. So, we will be working with growth 16. In case of growth 16, the time complexity is as shown in the slide, that the size of pi is this O of 1 and comma this time complexity of this verifier to verify is big O1. So, this part is done. Now let me talk about this security parameter, right? I just briefly touched it in the previous slide. So let us understand it more. This lambda is considered as a toxic waste. So let us see what I mean by that. The verifier, after generating this random number, must discard it. So this lambda should not get leaked. Fine. If the prover gains the knowledge of lambda, then it can generate fake proofs pi, which will get accepted even though the corresponding witness won't satisfy the circuit constraints. So, this is the reason why we want this lambda to be hidden. We don't want this lambda to be leaked out, and because then the prover can generate fake proofs. But if only one person is generating this lambda, and then the person's responsibility is very high. We all have to trust that specific person, that he or she must have discarded this lambda. So a remedy towards that is this multi-party computation. What multi-party computation allows, it allows that many players generate their own lambda, and even if one of them successfully discards it, then the protocol is safe. So suppose we 10 people are generating our lambdas, we can combine, when we are doing this part here, the first part here, we can combine all of our lambdas can be combined, and it is required that at least one of us have discarded it. So let me show you this. This thing is also called as ceremony. And let me show you this link which I have mentioned in the slides. Okay, yeah, you can see that. So this is that site which I'm at, ceremony.tornado.cache, and you can see here Tornado Cache Trusted Setup Ceremony. The ceremony is completed. Thank you for your participation. And all these people, these 1,114 contributors, so all they participated in generating that lambda, and this was like open. Anyone was allowed to put up their contribution, and we can see Vitalik, Gavin, etc. have given their contribution to make Tornado Cache secure. So, with this open nature, we can be sort of sure that at least one of these 1,000 or so participants must have discarded their lambda. Fine. There is also this zcash ceremony. You can look at it in YouTube. For the zcash, I think the participants were very less. Basically, I think 6, but they elaborately documented it, etc. So you can see that on YouTube, zcash ceremony. So so multi-party computation is allowing the safety here. Now, regarding this Circom Snarkjs toolchain, this pipeline that we have to understand, where does Circom fit and what is the, use of Snarkjs, etc. And to, to get a broader, the eagle eye view about what all tools and how we will work with them, I have created this diagram, which is, this whole thing will be on GitHub. So GitHub repo will be shared in the description. Somehow it will be shared, and in that GitHub repository in the presentation folder, I have this file. This slide will also be in that GitHub folder. Fine. So let me open this diagram which I created. Okay. So yes, you can see this diagram. So we have this Circom. To that Circom, we will write a circuit, right? We will of course write a higher level description of the circuit. We won't work in these little gates, etc. We will write a high level description of the circuit, and Circom will do the rest. If to the Circom compiler I give this flag r1cs, then it will generate this rank 1 constraint system file, r1cs file, right? And to this r1cs, you saw that we insert lambda, right? We insert lambda to get that proving key and the verifying key. So what the smart people have done, that for this part, like there is, if I were to say, in this computation, like this z key that we have, this z key is that your proving key and the verifying key. Though these both, proving key and the verifying key, is in this z key file, right? But to do everything from the scratch, at least some part of it won't require that we call all the participants, that hey everyone, come do your contribution, make a protocol secure. For that some part we need not do, and for this some part we can use the pre-generated file. Basically, if I were to show you with the help of a diagram maybe, so let me just open that software. Just a second, I'm opening that software. Okay, so let me just move to this window now. Okay, here I told you that we need this lambda, right? So that we can make our protocol secure. So this lambda thing, so what the folks have done is that, you know to this lambda part, we can think of it is as in terms of two things. We can say some private thing and one public thing. So this is sensitive. This private thing is what is sensitive, and public thing is not. When generating this lambda, you can think of this lambda as this private thing. In this protocol, when we are generating, we did this S, which was taking the rank 1 constraint system, and the lambda. So that lambda you can think of as private thing. Once we have done this S of R1 CS, comma, this private thing lambda, we are getting this some public thing, right? Now another person will do this again, this S of R1 CS. Suppose this was lambda 1, then this lambda 2 to generate another public thing, right? And so on, all these participants will do, and this is combinable using multi-party computation. Somehow, I have not explained how exactly that math works, but somehow we are able to combine them. And only if all of these lambda i's are leaked is when the protocol becomes unsafe. But what that this diagram which I showed you earlier signified, that for that particular phase, this public thing was not dependent on this circuit. Folks are able to abstract some part of it out so that this public thing generated was not dependent on this circuit, this R1CS. So if I go back to where I was, yeah, here. So to that file, we take some previously generated ceremony file, we feed it in our Snarkjs, and this we are using the growth 16 protocol. Fine. So to the Snarkjs, we specify growth 16 protocol, and it takes these two files to generate this. This contains proving key and verifying key, but here is where we must add contributions. This is where we will have contributions like this. So this is called phase 2 contributions. This is where we will need help to make from other people so that we are trustable, and then we will get our final z key. So this is what will which will contain our the private key and this verifying key. Here, if you want to separately export the verifying key, Snarkjs provides that feature. So to the z key, to export the verification key, you can do that. We will when we will write the code, so at that time it will become clear. So we get this verification key. So this part I will explain. First, let us also see this wasm file, this web assembly file, right? This is used to generate our witness. So how do we generate the witness in the circuit? Suppose this circuit, if I know the set of inputs that I am giving to the circuit, so here x1 x2 and 1, once I know, once I provide the set of inputs here, then all the intermediate signals, the output of this plus gate, and the final output signal, that is known to me, right? So once I give the set of input signals, I will know the intermediate signals and the output signal. So if I go back to where I was, yes, here. So to this WebAssembly file generated by Circom, we give this input file. So only inputs to the circuit need to be given. Intermediate signals and outputs will be computed. So we will have this, generate witness file. It will, this will, generate. Sorry, I just missed one thing. When we are using this WASM flag will also generate this generate witness file. Snarkjs also has a feature where this generate witness file, we need not basically use this generate witness file. The Snarkjs also gives that functionality. But the main use of this WASM flag is not this generate witness file. The main use of this WASM flag is this circuit.wasm to get this circuit.wasm file. Now, to this, and when we use this wasm flag, it will also generate this file, generate witness. But as I told you, even if it was not generating this generate witness file, there was another way also, but let us not bother about that another way. So to this generate witness file, I will give my inputs to the circuit and this circuit.wasm file, and then it will generate this witness, right? So you can think of this wasm as like computational trace. So it will do the computation, etc., to get this witness. But this is not what we want to reveal. We want to reveal the proof, right? So from this z key containing, we will take this witness file. Also, if I show you back the slides part, let me go back there. You can see here that the prover was taking that proving key and the witness, right? So that is what we were doing. We are doing here. So let me go back. Okay, here. So from this z key, we will take the proving key. Basically, instead of extracting the proving key, this whole z key file is inserted in case of Circom Snarkjs toolchain. So we insert this z key and we use Snarkjs with this growth 16 parameter, and of course this proof parameter to generate the proof. It takes, this command will take two inputs, the witness file and the proving key. In case here we are providing this combination of proving key and the verifying key, and then it will generate two outputs. One is this proof.json, which is what we need actually. This public JSON is the public signals. So public inputs and the output of that main component and the public input of that main component. But this public JSON is not that relevant for us. Even if it was not generating, it was fine. What is mainly needed is the proof.json file. Now you have seen how that verifier verifies. So the verifier needs the verification key. So that is what we will provide. By the way, this, yeah, I have told already that this diagram is also in that GitHub. So you can see it later also. So the verifier will take the verification key, it will take the proof, and it will also take the public signals, just like what I told in theory. So we will provide all these, and we will use this command snarkjs growth 16 verify to get the verification result. So it will let us know whether the proof was valid or not, whether proof was valid or not. So also, where did we use the smart contract here? So to generate that smart contract thing, we from this zkey file we exported the verification key. We can also export the verifier contract. So using this command snarkjs zkey export solidity verifier, giving the input as this zkey, we will get the verifier.sol file. Now we can instead give inputs to this verifier.sol file here, this proof.json and the public.json. First of all, we will of course need to encode them in a suitable way. I mean, this is just a helper utility function. You can of course do it yourself if you're smart enough, but this is the helpful utility function. So snarkjs zkey exports already call data. It will present them using these two files. It will generate the like output of this command will be the suitable input parameters that we can pass to this verifier.sol file, and then this will return a boolean telling true or false whether the proof was valid or not. So this is what I wanted to cover in the theory part. We will see further as we will write our application. So in these slides we were here, we saw this, and then now we will do the hands on. We will start, I will explain the Circum part next. So let's do that, but first let's also take a 5-minute break so that everyone is at ease. So let us take 5-minute break and I will be back after that. Okay, so the 5 minutes are done. If we move on, what I want you to do is first install this Circom thing. So navigate to this link, this docs.circum.io, getting started installation. Basically, visit this docs.circum.io, and from then on, it will be easy to navigate to this getting started. And the first section is this installation. So to install, what I did basically, first they have mentioned very simple way of installing. So first use this command to have the Rust available in your system. So this they are mentioning that it is for Linux or Mac OS. So for the Windows, you will have to see how to do it. Mine is Mac OS, so it worked very easily for me. We need to install Rust because the Circom compiler is written in Rust. This is sort of irrelevant, but even otherwise, if you are having the version less than 10, so kindly update it because they require the updated version. Once you have this done, use this to install. I mean, first of course, clone their repository, then enter the Circom directory and use the cargo build to compile like that. Now, this will take around 3 minutes, so let it happen. I will just explain the theory part of the Circom. So let it take the 3 minutes which it wants to take. When the command successfully finishes, it generates the Circom binary in this directory target/release. You can install then this binary as follows. Fine. The previous command will install the Circum binary in this directory. And then the Circum part should be done. So what I'll do, I'll just pause here for 30 seconds for you to, just navigate here and have it all set up. So I just pause here for 30 seconds and then we'll be back. So I hope that you were at least able to reach at this command, which is taking around 3 minutes to complete. So let us start with a simple circum circuit. Here it is my terminal. So what I'm going to do, I'm going to just create a directory named backend and I'm going to move into this directory. Now I'm just going to initialize the hard hat environment here. It is not at all required, but I just basically we will need some npm packages and I don't want to work with empty npm init type of thing. So I'm just initializing it here using you can use this command, this npx hardhat. In case that hardhat won't be installed, then it will install it, so not an issue there. So I'm going to hit enter to all these and wait for it to get completed. We will also be using a plugin known as hardhat Circom. Basically, as you will see in this session, that when generating all this zkey, wasm, etc., it is quite cumbersome. And for the development phase, we would like to have it automated. So this is where that hardhat Circum plugin comes in picture. There are other helpful tools also which the people have released. You can look into, you can just search about it. But for this session, we will be using Hardhat Circum plugin of the Hardhat. But yeah, but for the initial part, we will reach that Z key stuff without using that plugin. So as such, Hardhat is not needed, but let's have it installed. So this is done. What I will want you to install next is this npm install Circumlab. Fine. I want you to have this also installed. So this part is done. So let us create a directory named with circuits, right? So let us create a directory named circuits. Let's move into that directory. Let's create a file named multiplier.circum. This example I will take straight from the documentation. It's a very simple example, and we will be able to understand the basic syntax of the Circom using this example, right? So I'm just going to, open this file now. Actually, instead of opening that single file, let me open this whole directory, the Visual Studio Code. And then I can just move into that directory here. So this is the directory in which we are. So for this, what is this log.sol? Oh wait, where is my circuit folder? Yeah, this is my circuits folder. I think Hardhat upgraded their initially before it used to be some other contract. Anyways, let us not go into that. So to this, I'm going to now paste a code which we will try to understand here. Just give me 1 second. Okay, this is the code. First line, if you notice, Pragma Circom 2.0.0. What we are doing here, as per my understanding, that we are explicitly specifying the compiler version, basically with what compiler of this Circom we should compile this file. So you would have downloaded the latest version. Basically, when you are downloading, installing this Circom compiler, that compiler is like a set. It doesn't have just the ability to compile with version 2.0.5. It is also able to compile with 2.0.4, 2.0.3, and so on, and also 2.0.0. So when I'm compiling this file using that Circom, how do you compile? If I show you, just give me 1 second. Okay, here. So you can just mention after this Circom the file name, right? But if you do just like that, it will just tell you that circuit is compilable. Fine. You will also, and no file will be generated. If I show you, we just have our initial file. So what you can do, you can specify what you want, R1SS and this wasm thing, right? So now if I see, those two things have been generated. One is this R1CS and the other is this JS file. And if I show you what is the version, we are using 2.0.5. And I believe I compiled that file. Yes, I also checked that I compiled that file using version 2.0.0. So even though when I'm doing this circum minus v, it is showing that it is 2.0.5, but the way you should see is that it is actually having the support to compile a file using version 2.0.0, 2.0.1, so on, and also this 2.0.5. So to that file, if I change, like if I also show you to that file, if I make this 2.0.5, and now if I compile here, it has successfully compiled. Now let me also change it and make it 2.0.6. Let me just quickly show you that I have indeed made it 2.0.6. As you can see here, I have indeed made it 2.0.6. And now let me try to compile it. Then you can see that version 206 is not supported by the compiler which you are using. So I hope that clarifies the pragma statement here. So let's move back. Okay. Now this is the line which I want you to pay attention. Is this is the main component. This is where, like, we can have another templates, some whatever. I mean, there could be multiple templates in the program. You can think of these, as sort of a composable block structure. So you can use the template. Now here this could be, another, like, we can multiply three elements here. So let me create an intermediate signal, and I will name that signal as inter. So to this inter, I will explain what this means shortly. So don't worry about that. And yeah, okay. I mean, we can create multiple templates, and then at the main, we are specifying that we are using this template. And when we this composable structure is such that this multiplier 3 could indeed use this multiplier 2 as a component. Fine, but let me not do that in this example. Let us focus here in this code. Fine. To this main, we are instantiating this multiplier 2 thing. So this is that multiplier 2 thing. It is having this input signal a. Notice how we specify the input signal. We first of all specify that it is a signal. Signal is immutable. Once this a has received value, you cannot change it. There is something known as var. So in case you want mutable things, you should use var. Signals are immutable. We specify whether they are input or output, and in case we don't use this keyword, either input or output, then it will be an intermediate signal. So here, like, I have this intermediate signal which I have named as inter. Fine. There is just one thing which I want to do. Give me 1 second. Yeah, okay. I wanted to, pull up that YouTube window also. Fine. Now, in this multiplier to circuit, if you look, we are giving it two inputs, and we have this output C. As such, this output will be private, but since the main component is using this as a template, this signal C would be public, right? All outputs will be public. Now, when you are writing the circuit in Circom, you should think that you are writing two separate things. And this distinction, basically, the constraints part is something which you should pay strong attention towards. Fine. Like constraint. Now, if I tell you the constraint, this is a constraint. I type the C followed by these three equal symbol, and then this A star B, right? I just commented this last line. How do you put comments? You use these two forward slashes. Fine. Use these two forward slashes to write a comment. And now if you want multi-line, this was the single line comment. If you want the multi-line comments, then use this syntax. This is just like in C or C++ also, in case you are familiar with that language. Fine. Now this is the constraint here. What I am specifying that the value of this signal C should be A star B. Fine. Now I would also like to, in this circuit, for instance, in this circuit, I would also like to, assign a value towards C, which will be using this. Basically, you do this C, this less than symbol, and then these two dashes, and then you do this A star B. So in this line 7, I am assigning to C this value A star B, and then here I am constraining, I'm putting this constraint that C should be equals to A star B, and instead of writing these two lines, Circom provides us the ability to write them together using this less than and then 2 equals like this. Using these two lines are combined into a single statement. And it is also advised that we should use this as far as possible. I mean, as much as possible. Instead of, I mean, this part should be avoided. This single dash part should be avoided, but sometimes it is also necessary. Like, but that thing I will show you when we will see the is zero template. I plan to show that is zero template also to you. So that is something which we will see there. Okay. Now, uh, regarding this input signals also, as the circuit it is now, these input signals are private, but you can make them public. Like if I show you how, when you are instantiating your component, you can do this. In this curly braces, you can use this public keyword and then specify which of the input signals are public. So if I do A comma B, in this case, these like all the signals will become public. I have mentioned that A is public, B is to be treated as public, and C is also public. C is public by default, For the main component, output signals are by default public. I can leave it like that and specify that only a signal is public. So in this case, the verifier, suppose that the verifier takes one of the input parameter A, and of course verifier, this C is also public. So suppose it also takes C. Suppose the verifier puts C to be 33 and A to be 11. Okay, C 33, A 11. Since these are public, verifier can put them. The prover will have to prove that the prover knows a signal B such that A star B is equals to C. Notice that, I mean, this constraint part is very important here. Using this constraint, I mean, when we do this C assigning value A star B, this is, has been done, like you can think of it like that prover is able to, generate the witness, but anyone can write their own circuits, and in that circuit they might do C assigned something else. But what will save us will be this constraint here, that C is indeed constrained to be A star B. This part, basically what matters to the verifier ultimately is the constraints. Like if I go back to our diagram, maybe it's better to, emphasize this so that it becomes more clear. Just give me 1 second. Okay, here, yeah, here you see For the verifier knows the public signals and it does not take any other signal. What it is taking as the proof. What verifier wants that whatever proof you give, those constraints which we have satisfied, which we have specified, get satisfied. So basically, the constraint satisfaction is important, right? The assignment part is not that important in the sense that a prover can write some another circuit where it is assigning something else. We are not bothered with that. Verified has the verification key using this constraint system which it got, right? So we are saved there. So what matters to us ultimately is the constraints. Those assignment helps in generating these computational trace, the WebAssembly, and then which helps us to give this witness. Fine. So the constraint part is what is at most important. So let me also go back to my code window. Yeah, here. Fine. Now in case I remove this, the part which I had, and now only the output signal is public. So if the verifier sets the output signal as say 33, then the prover will have to prove that it has two input signals a comma b, such that the constraint that c is assigned equals to 8 star b is satisfied. Basically that 33 should indeed be this a into b. Fine. That is the you know what this circuit will specify. Now you remember we did this command npm install this Circumlab, right? Now if I go to this node modules, we would have that Circumlab here, circuits, and I think comparators, right? We have this is zero template. So let us now try to understand this is zero template. So let me also create a file. So I'm just creating that file. Okay, it's created here. And I'm going to, copy this code here. One thing which I would like you to notice is that all these templates, the styling is such that the first letter is capital. So in case they have put the first letter as capital. Fine. So and so it's the instance of this is zero. So what this is doing, maybe I should put this comment here. Out signal is set to 1 in case input signal in is 0 and is set to 0 otherwise, right? So in case this input signal is 0, what I want, fine, what the verifier wants, that the output signal should be 1. And in case this input signal is positive, and of course in that field, that zp field, what we want this output to be set to 0. Now when writing these circuits, I want you to forget about this thing, this part and this part. I want you to forget about this part, but focus on this, the constraint thing. Fine. Now for this, you can see that output is either 0 or 1. Fine. So one of the constraint could be this, that out minus 1, and this out is constrained to be 0. One of these constraint can be this, because the only way this equality is satisfied is when either this part is 0, this factor, which will imply out is 0, or when this factor is 0, which will imply out to be 1. So this is the one of the constraint which you can think. And what are the other constraints which you can think? You will notice that they have not used this constraint in this example because this was redundant. This was not needed. We have only these two constraints here, this line number 12 and this line number 13. And in this line number 12, we have one constraint, and this line number 13, we have another constraint. This constraint is not used here, but you will see such constraints in practice. But for this example, this was not needed. But this is also one of the way, but this will just give us one help, that output is constrained to be either 0 or 1. We need one more thing. We need the logic. We need the constraint that it is not the case, we should not have both input and output to be 0. That should not be possible. If input is 0, output must be 1. And in case in case, the input is some positive, the output should be 0. Fine. So how they are doing it? So let me show you like their logic, and this will make sense also. Then we have this inverse thing. Inverse signal is, this is an intermediate signal defined here. Notice that they are doing this ternary operator here. Fine. Now, if ternary operator is possible, you might think that we can, simply do this, that in, if, whatever, like it's equal to 0, you put 1, otherwise you put 0. Fine. You might think that this is possible, that if ternary operator is allowed. Well, the fact is, the constraints have to be quadratic expression, and this ternary operator is not a quadratic expression. First of all, yeah, that was also fine. So this is not allowed. So that is why they are using this single arrow, not double arrow, because double arrow will imply the presence of constraint as well, and we cannot put a ternary expression in a constraint. Fine. So that possibility is ruled out, and that is why they have single arrows here. Now, what is this 1 by in? Basically, this is of course the modulo inverse, and I think maybe I should spend some time, very little time, to explain a bit about this modulo. As such, this is something prerequisite, but let's me just tell you a small example. Consider this field zp. Sorry, let's make it, let's make p to be 7, so that we don't have much elements to bother with. So this will be this 0 1 2 3 4 5 6, right? Every addition you do, you will do modulo 7. So 6 plus 1 will be 7, which is equals to 0 when we are doing this modulo 7. Fine. Now what I want you to do is find the inverse of 2. So what is the inverse of 2? Inverse of 2 is an element x such that when you multiply that element with 2, you get 1 modulo 7. So can you find any element here such that if you multiply 2 with that element, you will get 1 modulo 7? So that element is 4 here. So 4 into 2 is 8, and 8 mod 7 is indeed 1. So this x is 4. In case, since we are working with prime fields, an efficient way to find a modulo inverse is this. You do to the power, p minus 2 modulo p. So in this case, to the power 7 minus 2, 5 mod 7 we have to do. This is equals to 32 mod 7, and 28 plus 4. So this is 4 mod 7. So same value. This is called as, you can just Google if you want, Fermat's little theorem. And in case you want a revision about what is a field, field is a commutative ring with unity, such that every non-zero element is a unit, basically has an inverse. So I know this was a mouthful. I was just trying to, give a small gist of what is field, in case somebody have, naive idea, at least have studied modern algebra in past. So I mean, that's fine. You may not know that, so you can just Google that. So this is the modulo, I mean, this is the inverse of 2 in this example. Moving back towards our code. So what this 1 by in is doing, or for that matter, wait a second. And for that matter, any expression like this, a by b, what this is, equivalent to a star inverse of b. This is what it is. So in our case, suppose I mean, I hope like 1 by 2 in our case will be 4, because that is the inverse of 2. In 7, prime field 7. But here, the prime is something very big. It's a 254-bit big number. You can see that I might show you also. So I think it's called baby jub jub prime. So fine. Okay. So here we saw that because of this ternary thing, we cannot use this double arrow. So they have this inverse specified here. But as I told you, this single arrow means nothing. This single arrow is helpful in generating witness, this all this wasm, etc. But for us, for the verifier, it would mean nothing. What would mean for the verifier is this, that for the out, what they have done, they have multiplied this number with its inverse so that it will become 1. Any for Of course the inverse exists for the non-zero element. So for the non-zero element, the inverse is exists, and when they are multiplying with it that inverse, so I mean, assume for now that n is non-zero, so multiply with its inverse, you will get 1. So minus 1 plus 1, you will get as 0. That is what they have assigned to the out. But as I told you, this inverse can be anything. For the verifier, I mean, anyone can write circuits, so this inverse can be anything. What we have is just these two constraints. Now let us brainstorm and think that just by having these two constraints, what we want will be satisfied. What we want, that out signal is set to 1 when input is 0, and no, I mean, like, out signal is 1 when input is 0, and out signal is 0 otherwise. So let us do that. Suppose that input is 0, then output should be 1. Suppose input is 0. Now if input is 0, this whatever be the value of inverse, let me not bother about it. Since in is 0, 0 into anything will become 0. So this expression will become 0, and out would indeed be 1. That this constraint will as such like also make out to be equal 1. Fine. So that this constraint is satisfied only when out, I mean, this will indeed this constraint in itself will imply out is 1, and this thing, if we do 0 into out, which is 1, that is again 0. So that constraint is satisfied. So let us now think of other possible scenarios. What this scenario gave is out to be 1. Now, when out is 1 1 1, like if out is 1, now if we look at the the converse, the reverse way. So if out is 1, this is also 1. So this entity will become 0. The constraint as such will specify that this entity is 0, and this constraint here wants that one of them to be 0. And what I told you was, if I remember correct, I think I told you out is 1, right? So out is 1. So what we will have that in to be 0. Fine. Now let us look at for other case. Suppose in is 3, 4, whatever, some positive number. Of course, less than that, less than equal to that baby Egyptian prime. I mean, of course, less than that prime, because modulo that prime we will get 0. Now that in is positive, and we have these two constraints. This constraint will, of course, then imply that out has to be 0. So with the help of this constraint itself, that out will become 0. So what we will have, that 0 minus in into something plus 1. So this will also imply that inverse is indeed the inverse of this in signal. So I hope this part is clear. One thing more that I would like to add here, that it won't be possible to, also, like, one thing here, I did not explain this ternary, right? So what this ternary is doing, that if this is non-zero, basically some positive number, you find the inverse, fine. And in case it is 0, you set the inverse to be 0. So 0 into 0 will be 0, and then this 1 will get assigned to out. I mean, this part is as such not needed, but they had to put something here. I mean, in the case when n was equal to 0, so that is why we have this case. One more thing which I would like to add here is that, if we do something like this, I mean, forget the context here that we are in this is 0, but for the general thing, if we have this constraint like that, then this won't be valid. This is not valid as it is not quadratic. So instead of writing this, what you can write is this thing which I'm going to show you now, that in star in is constrained to be 1. So these are the cases in where you will need to use, the single arrow, because via single arrow you can first do this, and then using that triple equal symbol, you can do that. This in star in equals 1. Of course, I mean, for this simple example, you could have, yeah, no, sorry, not for this example. So this is indeed what you will have to do, because when you're using this assignment operator, you use this for a signal. So here, this inverse is the signal which we are putting this assignment operator to. You don't put any expression here, but instead you put a signal here. So to this signal, I am assigning this 1 by inverse, and then I can do this inverse star in equals 1. So that is how you can, put up a constraint. And this is the example where you will need to use the single arrow. Fine. Also, this exists. I mean, we could have as well, did this. So this was in also valid. I mean, this can be reversed. That is what the Circum is allowing us. Circum also allows this thing, this operator to be reversed. So just ease, convenience ease, the Circum is providing us. Somehow space got here. Fine. So these are the two circuits I wanted you to see. Also, let me see whether there is one more thing which I would like to cover or not. Also, the documentation which is present in the Circom website, that is very, very small. I mean, I believe that you can finish that documentation in less than an hour. Personally, it took me less than an hour to finish the documentation. I mean, after covering, the basics here, which we have done, seeing the documentation will become very easy. It will be a breeze. So let me just see whether do I have one more example. I thought I had one more, like as an homework, which you guys can see. Yeah, I found it. So I'm just going to put that here. So this is the circuit which I would want you to, take up as an homework to understand the working of this circuit. But if I were to give you, a gist about it, first of all, this template is taking this input parameter, and this input parameter has to be a compile time constant. So here we have specified in this file itself as 3. So this n is 3. Basically, the point here is to get the bit representation of this input signal, provided that input signal is, it should be, yeah, less than equal to 7, provided this input signal is less than equal to 7 to fit in the 3-bit binary. they have this wars here. So var is mutable. You can change the value of var. You cannot change the value of signal once you have assigned it. So we have this for loop here, just like in other languages. Also, I find it funny the way they are writing, their code. If you look at it, there is a white space here. I mean, but you don't see white space here, so they are not consistent. Also, after this subtraction operation, you have this one, but otherwise they are using white space. And this inconsistency is not in just this documentation example. In the actual code I've seen, when I was going through, I could see such inconsistencies. So I wonder why is that the case. All right, so this war thing is there. Now they are having a non-quadratic expression, so they are doing this. Here they are using that trick which I showed you to constrain that output bit should be either 0 or 1. So this is what this thing will constrain. And then ultimately what they are putting is that the final value, basically what they're doing, that once they have this output bit multiplying with the corresponding power of 2, first of all this starts with 1, and then to the power 0 is 1, so that is why 1 here. And then 1 plus 1 is 2, so then e2 will become 2, and then the third iteration 2 plus 2 4, so it will become 4, like that. So a cheap way, I mean, from cheap I mean the computationally easier way. And also we are using e2 again, so this is a very smart move here. So that is what they are doing. So once they have this LC1 computed, in the last, they are mentioning this constraint that LC1 should be indeed equals to this in. So, and they are also using arrays here. This out is an array. And when instantiating this component, they are specifying the public signal as in. So this is the example which I want you to, explore further. I mean, yeah, as such, I think I explained it fully. So this is the example I wanted you to have, clear understanding of. Okay, so let us go back to our multiplier example. Yeah, here. So let us go back to this multiplier example. Let me fix few things. So the setup is, as I've told you, this C will be the public signal, and we have to find the factors. So suppose this is from the documentation. So suppose I fix C to be 33, the prover must prove that it has two factors a comma b such that their product is equals to 33. That a could be 1 and b could be 33. So I mean, as such, this is a very easy problem for the prover. I mean, not, but I mean, it's a very simple example, not that relevant in practice, but I want to show you the compilation part of it. So let me go back to the terminal here. Okay. So this command I showed you, right? So this circom multiplied, I mean the file name, and then we want these both files. We want to generate the witness or wasm, and we also want to generate the keys, proving key, verifying key, so that rank one constraint system. So I have generated that. Okay. So let us generate the witness first. So I'm going to go to this multiplier file. So we have this generate witness and this multiplier.wasm. So let us use them. I'm going to put up the commands, and you can see what are those commands when I'm putting them in the terminal. Let me also go there. Also, let me just show that here. Basically, in that Circom website, in the getting started, you can see all these commands also. So in that getting started page, these commands are also mentioned there. So just give me 1 second here. First of all, to generate the witness, I told you that we need to give the inputs to the circuit. So let me do that. So Let us name it multiplier.input.json. It has to be a JSON file. And if I go back to my Visual Studio Code and open that file, I'll just show you that file after putting the values. Okay, so I created this multiplier.input.json file. To that JSON file, I've specified my inputs. So A is to be 3. Here this A is to be 3 and B is to be 11, so that the output is indeed 33. Fine. Let us now move on to our next step. Next step will be this, which have mentioned here. So we will use this generate witness file, giving it our multiplier that thing, and then this is this, and the output I'm going to name it multiplier dot witness. So finally we have our witness file that we wanted. Also we use this JavaScript file, right? Generate witness. The we also get provided with the C++ file, which you can use in case you have a very big circuit. So for the big circuits, that would be computationally cheap. So that can be used in case you have the big circuits. You will have to use the compilation, like just how we used WASM. You will need to use the compilation flag dash dash C to get the C++ file. So now if I go back to that pipeline diagram, here we did this thing. We generated our circuit file. So we have reached this point. So now let us use this R1 CS thing. And to use that, if you go here, github.com/iden3, the one who are maintaining and have created this Snarkjs. So in that Snarkjs, they have all these, steps which you can follow. One thing which I would like to say, that here we will use a ptau file, right? Fine, this is what we are going to use. So either you can download a file or you can just use this command to have that file for you. Now they are specifying this contribution. So in case you want to add robustness to this, add more contributions, you can do this. I personally don't think it to be necessary. Then they have this command verifier to verify that everything is going fine. And this is something which I would like to spend some time on, this random beacon. Now, what is the case that the ones who have written the research paper about this random beacon, according to them, what they're saying that it was easy to prove the security of the protocol if you provide the random beacon, but they're also saying that most likely the security will hold even if this was not provided, but they did not have time to prove it. That is their statement if you will read the research paper. So, as such, it is safe to apply the random beacon. So, what is this random beacon? The understanding what I have of this random beacon, basically some value which is not known before when doing all these things. That random value can be, say, a block hash at a particular date. I mean, Bitcoin block header hash at a particular date. So you can use that at a particular date. But the issue with that is that it has a bit less entropy. What I mean, because of the high difficulty in mining, you know that the first few bits of that Bitcoin header will be zero. I mean, this is what the mining difficulty is all about, the nonce thing. You can just search about it in case you don't know. So the first few bits will be zero, and then the entropy, therefore, basically that randomness, you can say, will be in those remaining bits only, the remaining bits which need not be zero. So that is why that perhaps is not the good example to take that header as a Bitcoin header. But what I think the Zcash folks took Bitcoin block header when in their own implementation. Also, there is this verifiable delayed functions. Basically, suppose you are a miner and somehow and the protocol thing is that in case the block hash is even, you will get the reward, right? Suppose the smart contract whatever is implemented like that, that in case the block hash is even, then you will get the reward. So now once you have mined the block, if you see that it is even, oh sorry, if you see that it is odd, then you can discard it, right? As a miner you can discard it. You know that at this block hash the winner will get the, I mean I will get the reward if the block hash is even. So in case it is odd, you might discard it and try to have wait to try to mine the other block. Now a way to circumvent it is that this value which the miner was using, as such if we use the blunt block hash header, then the miner can easily see whether it's even or not. Why not have it a further computation? Basically the miner will try to do the more computation towards it so that it takes reasonably more time than 10 minutes. In Bitcoin protocol, you know, every block is produced, I mean a block is produced every 10 minutes. So if case that computation takes reasonably more than 10 minutes, then this thing will get, you know, somewhat hampered. Some more thought need to be given in it and you can give that thought. But this is the understanding, you know, which I have of this random beacon. So now let us just quickly do all these commands here, right? So I'm just going to move that multiply.witness file towards outside. So that my file is outside. Oh wait, sorry. I just forgot to set the focus to the terminal here. So outside my this multiply.js folder, I have put this multiply.witness file, right? So now I'm going to put this command. This thing is done. And I mean, we did that. Now then contribute, second contribution, third contribution, verify, random beacon. All this is not as such needed, but I mean, you can read the description of this command in that file. They have mentioned the description of what a particular command is doing, right? So this, sorry, yeah. I mean, I'm not being, you know, giving it actual random thing here. So now we have this command for the phase 2 thing to make it ready for the phase 2. So I have pasted that command here and it's taking some time to compute it. Taking quite good amount of time. All these commands are from that repository which I just showed you. So you can just have a look at it and use those commands from there and also read their descriptions from there. Tomorrow we will use hard hat Circom plugin so that we won't be, it won't, I mean these all these commands we will need not write. This all will get automated. So that's a cool thing about it. So what was the command which I inserted? This one, right? Preparing it for phase 2. Fine. If I move next to what it is providing me, we have all these things: circuit, compile circuit, that all we have done. Witness we have done. Then beta beacon is what I had. And when did they make it final? Just let me see. Okay, in this file itself. So I have this port final, right? Like if I look, I did put that prepare for phase 2, right? But somehow it is not showing me. Okay, it is now showing me. Yeah, so I did put that prepare thing. So fine, that part is fine. Next, they have this setup. Now we have these two algorithms. If you look at that page, we have two algorithms. One is growth, and one is uh, this Plonk thing. Plonk is a bit more suitable in the sense that it does not require that phase 2 contributions. But in our case, let us go with growth 16, and it needs this r1.cs file. So did I have this here, r1cs? Yes, I do. So I can use this. Just need to make it like that. So that part is done. So hopefully let's finish it. Then they have this contributions. So I'm not going to do that here. Then they also have this random beacon. So let me just do that random beacon thing here. Okay. So that random beacon thing is done. Now let us do this verification of, this exporting the verification key. So what did I name it? Circuit final. Yeah, the command named it circuit final. So let us use that that name only, circuit final. Now let us quickly create the proof from that documentation itself. They're mentioning that proof thing. So I think I named it this. It will generate these two files, proof.json and public.json. So if I show you that proof.json, which is what we will send, we have this, and that public should contain 33. As such, it was not required, but they have done it. So now let us verify this proof, right? The ultimate thing which we were waiting for. So to this proof, pass the verification key, the public inputs. Public signals should be the better word, and then this proof. So let us hit enter, and it is giving us okay. So yes, the proof was indeed valid. Now, if you do some slight changes in the proof, you will see that it won't get passed. So that is all what I wanted to cover today. So congrats in making this far. Tomorrow is when we will do the smart contract part. So I haven't done smart contract part here. That is for the tomorrow session. So thanks for joining in, and this is where I will end this session.
Thank you, Saurabh, and thank you everyone who have who joined the session and supported. Okay. I know this is this was longer one, but yeah, like this will help you understand zero knowledge, circum, and all. So thank you everyone, and thank you, Saurabh. We'll meet tomorrow at the same time, like 3 p.m. Okay. Yeah. See you then. Bye.